Hello everybody, welcome to the channel. Today we will speak about Gaussian quadrature and we will see the theory behind this. Gaussian quadrature was invented by Carl Friedrich Gauss, that you see in this picture, a famous mathematician who lived in the past. Let's move on. What is Gaussian quadrature? A quadrature rule is an approximation of a definite integral of a function, which is usually stated as the weighted sum of function values at specific points within the domain of integration. An endpoint Gaussian quadrature rule is a rule which uses endpoints. N can be any number, 1, 2, 3, or anything, and it will yield exact results for polynomials of degree 2n minus 1 or less. So if we are to integrate such polynomials, we can choose the right number n, and then we can have an exact solution to this problem. Usually, our formulas are expressed in the interval -1 to 1 that you see here. And so the rule is stated as you see here. So the integral from -1 to 1 f t dt is equal to a sum of some values of the function at specific points ti multiplied by the weights wi. So the difficult task of calculating an integral becomes an easy task of just calculating some values of the function in this interval and then multiply these values with some weights and do the sum, and then you have the approximation. So this rule will give us exact results for polynomials of degree 2n minus 1, which means that by using one point, only one point, we can get exact solution for first degree polynomials, which is not so good, but it's only one point. Then by using 2 points here, we can get accurate solutions, exact solutions for polynomials of up to third order. And similarly, with 3 points, we can approximate exactly polynomials up to fifth order. And by using 4 points, we can go up to 7th degree polynomials. And it goes on. So a quadratic rule will work very well if my function f is well approximated within this interval by a polynomial of degree 2n minus 1. In this case, I can get very good results. Here we see a comparison of the Gaussian quadrature rule, which is here, with the trapezoidal rule, which is on the left. And you can clearly see that the trapezoidal rule is simpler. You simply connect the 2 points here, and you take this area here as your integral. While, for example, if we use a Gaussian quadrature scheme with 2 points here, then we simply calculate these values, we'll multiply with the weights, and then we have a better approximation of the integral here. So let's see what are these points that we need to calculate our function on. If we use one Gauss point only, In this case, and we remain in the interval -1 to 1, then the point is the central point. So it is 0, and then the weight is 2. So this tells us that if we use one Gauss point only, then we simply find the value of f at 0, and we multiply by 2, and this is our first approximation. If we use two Gauss points, this case here, then we have 2 points to use, which are defined here. The first point is -1 over square root of 3, and the second point is +1 over square root of 3. And these here are the approximate values, plus or minus 0.577, etc. In this case, we have 2 points, and the weight for each point is 1. So we simply calculate the function, the value of the function at -0.577. We multiply by 1. We calculate the value of the function at 0.577 plus and minus. We multiply again by 1. And then we add these two together, and we have the approximation with 2 points. Similarly, if we use 3 points, then we use again the central value of 0, which has a weight of 8/9, and then we use one value on the left, one on the right. So it is minus square root of 3/5 and plus square root of 3/5. And this is the approximate value of these points. And then for these 2 points, our weight now becomes 5/9. So this was the 3-point case. And if we use 4 points here, then again, we have our points here, and we have our weights here. The sum of the weights is always 2 in these cases, as you can see here. This is 1 point with 2. This is 2 points with 1 each, etc. So the values of the weight will sum to 2. So this is what we need for up to 4 points. These are the values that we need to use to calculate an integral. We talked about functions defined over the interval -1 to 1. Now we'll see how we can approximate functions given in an arbitrary interval a to b. So in this case, we want to calculate this integral here, which is defined over an arbitrary interval a to b. And to do this, we need to do a transformation. And this is the transformation over there. We substitute x by this, which has a new variable t. And in this case, x belongs to the interval ab, while t now belongs to the interval -1 to 1. By doing this, I take a new formula here, and I have transformed my integral to an integral which is defined in the interval -1 to 1, and then I can easily apply the Gaussian Quadrature rules. So finally, if we do these transformations, we will end up that our integral here from a to b is b minus a over 2 times this sum, which is the weights times the function values at these points, where again ti now is the usual values of the Gauss points defined over -1 to 1. And wi, of course, are the corresponding weights. So by doing this change of interval, I can now calculate any integral using this Gaussian quadrature rule. Until now, we spoke about one variable functions only, fx, but we can apply the same philosophy exactly also with two variable functions or functions of even more variables. Now, in this case, we have an integral with two variables s and t. So in this case, it is defined like this: from -1 to 1 for let's say s, and from -1 to 1 for variable t. And again, we apply the very same formulas, but now we work in two dimensions. So for example, in this case, if I want to apply a one-point rule, I will take only the 0, point here. While if I want to work with two Gauss points per direction, then I can go back here and I can read the values, which is -1 over square root of 3 and +1 over square root of 3. And in this case, I will have to work with 4 points that you can see here. So this point is here, for example, is, let's say, it is -1 over square root of 3, -1 over square root of 3, and this point here is 1 over square root of 3, -1 over square root of 3, etc. So I will work with 4 points because I work with 2 points per direction. 2 points in the s direction, 2 points in the t direction, leading to finally 4 points, 1, 2, 3, 4. In this case, w, the wi's and the wj's will be 1 for all 4 points because I work with 2 points per direction. Similarly, I can apply the same philosophy and I can find integrals of functions with more variables, for example, 3 variables, x, y, z, or anything else. And again, in this case, we saw an integral over -1 to 1 for s, -1 to 1 for t, but I can again apply the same transformations as we saw here, and I can transform any integral to this integral. So in fact, I can calculate any arbitrary integral from a to b and from c to d of my function fxy, let's say dx dy, by transforming this into another equivalent integral, which is defined from -1 to 1 in both directions. So I can apply the same transformations in the two variable function, and again, I can get the result. So this finishes the presentation almost, but now I would like to point out why Gaussian quadrature is important, and one of its important applications is in finite element modeling. In finite element modeling and finite element analysis, many times we end up to integrals. For example, when we want to calculate the stiffness matrix of a specific element, then we end up to an integral, which also includes matrices. So it's a difficult integral to calculate. And in this case, we can apply the Gaussian Quadrature rule, and we can get easily an approximation of the integral, which we can use to find the stiffness matrix. So many times we use Gaussian Quadrature due to its accuracy and easiness of implementation. As an example, I can show here a 4-node quadrilateral element, quad 4, in its natural system that you see here with the 4 nodes. And you can see that we will end up to this double integral here when we want to calculate the stiffness matrix of this element. So this is the integral. It needs to be calculated. It is not so easy, but we can easily apply the Gaussian Quadrature rule, and we can convert this integral to this sum, which in the case of 2 points per direction needs only to be calculated at the 4 points here. 1, 2, 3, 4. If I use 2 points per direction, then I call this a full integration scheme, which leads to 4 calculations at these 4 points that you see here. While if I use only 1 Gauss point per direction, which means that it is 1 point in general, then this is called a reduced integration scheme. So by using 2 points per direction, I have these 4 points. And if I use 1 point per direction, I will need to calculate the integral only here in the middle of the element. And I call this a reduced integration scheme. So in finite element analysis, Gaussian quadrature is very important and very helpful, and it helps us to calculate these difficult integrals in an approximate but quite accurate way. That was it for today. You can also check the exercises that I have uploaded with Gaussian quadrature that follow this theory that you saw. Thank you for joining.